All right, I'm going to put our countdown up here. And then we'll get started here in 23 seconds and counting. Eight, seven, six, five, four, three, two, one. We have ignition. And here we go on our way to Mars. All right, so that was actually just the launch from a SpaceX launch on Sunday, Crew 1 mission, where they sent 4 astronauts to the space station. And they all just arrived last night successfully. But today what we're going to talk about is Mars. Before we get into that, I just want to introduce the panelists that we have here. And before that, I even just want to talk about who we are. Who is this group? Why are we putting this on? So we're NewSpace Chicago. NewSpace Chicago is a 501c3 organization, and we're committed to building a community of space entrepreneurs in Chicagoland and the Midwest. Prior to COVID, we'd have in-person meetings every month, and we discuss a wide variety of topics. Different speakers would come and present on things, anything related to space. But now, since we're remote, what we're doing is a series of 3 sessions here to begin with, which are all related to this Mars project that I'll talk about here and introduce in a little bit. But this is, we're going to be continuing this online speaker series into the new year as well. And at the end, we'll talk about some of the upcoming speaking events as well. So without further ado, let's introduce the panelists for tonight. Here with me today, we have David Hurst. He's the CEO and founder at Orbital Transports. Jim Plaxco, he's a programmer, photographer, and digital artist. Constantino Miraculous, he's the director of structures at Thrust at IUC. Michael Story, managing partner of Beckett Solutions. And then myself, Nick Lindeke. I'm a product manager. I work for a software company called Intellis, and I'll be your host tonight. So let's talk a little bit about what the context is for this panel tonight. I'm going to be talking about this Mars City-State contest quite a bit. And if you're not familiar with it, let me just give a little bit of background to set the scene about what we'll be talking about here. The mission of this project is to design a settlement for 1,000 people on Mars. And more than a settlement, it's just open-ended to say, how would you create a society of 1 million people on Mars? And we have to decide everything from what food is produced, how they make clothing, what the shelters look like, how are all these things powered, what are the vehicles, transportation methods, and machines on Mars? And then how do we make it so that the least amount of things need to be imported from Earth? And what are the economic drivers to make this a self-sustaining, million-person settlement on Mars? And all of these sort of factors are around designing our city-state. And what we did is broke up this kind of like a thought experiment into 3 webinar sessions to present on what this group from NewSpace Chicago put together. And this was part of a contest sponsored by the Mars Society. I've got their link here in the bottom right. And this is it's just to get people around the world thinking about what it's like to build a civilization on Mars. Because if we don't start thinking about it now, we're never going to make it happen. And everybody here tonight and many people around the world feel like strongly about making that vision of reality possible. And that's what we participated in as a group, to come up with a paper and submit it to this contest. And it was quite fun to put together. And I think we had a lot of really, really fun conversations about how to solve technology problems, economic problems, social problems, political, etc. But tonight we're going to focus on technology, because the scoring for this submission was broken into those major categories, and 30% of that work was focused on the technical side. And the questions that they posed as part of this submission was, what engineering systems will be used and how will they work? Wow, that's so open-ended, right? Doesn't even begin to address the type of problems that we get to solve, but we'll get into that today. And although we have, there's 5 of us here tonight from the group that wrote the NewSpace Chicago submission for this contest, but there's quite a few more people who are involved. 17 people are listed as authors on our paper, and you can see some of their faces here now. So like I said, this paper that we put together, we called it the 1 million Marciane, humanity's next giant leap. And when we talked last week, we talked about the economic situations and the types of things we solved there today. Today, we're going to talk about the technology side. And, you know, I want to set the scene for just like the amount of thought and work that went into putting this together. And I think perhaps you'll like be inspired to ask some questions about this group here, because we've all thought about it quite a bit. So like I said, there were 17 authors on this paper. We spent about 2 months. It works out to be about 2,000 hours and only one all-nighter. We pulled it together in 11,000 words and 20 pages and a whole bunch of citations at the end, because everything we are reporting on and proposed is based on, you know, scientific fact and reality now, and then using our best hypothesis to predict what would happen 100 years from now in the future. And I'm going to set the scene with a few more facts and figures just to get everyone on the same page, thinking about where we're at in time and space in solving these problems. So the first stuff I want to show is when we're talking about technical challenges on Mars, we're talking about 100 years in the future on Mars as well. To get to 1 million people, it's going to take, we estimated around 100 years, give or take, for enough spaceships to be sent to Mars to carry people and also people natively born on planet. And this is what our civilization looks like spread out across Mars. Here you can see that I believe there's 10 cities spread out across the entire planet. And if you want to familiarize yourself with the map here, over on the left side here, we have Olympus Mons, everyone's favorite volcano, largest one in the solar system. Valles Marineris, an epic Grand Canyon. I think it's like 3 times as deep as the Grand Canyon here on Earth. And then the northern part, these are kind of the lowlands. And then we've got some major craters here, some more volcanoes. And we pose settlements here on places that were of economic interest for the resources that were relevant there, and also based on our hypothesis of where we think that people from Earth will go and land on Mars and settle separately. And I'm going to recap a little bit from the economic session, so you kind of like, if you weren't there at that one, you'll have a little bit of threads to pull with you. But what you see here on this map is many different city names in different languages. And one of the like main things in the background of our hypothesis for the future is there will be a lot of global players in this, in settling Mars. And from like an economic standpoint, that drives a lot of decisions with like what are public goods, because people's perception of that is quite different from around the world. Like what is the government type over Mars? And those things are very dependent on what people's backgrounds are and belief systems are. However, when we think about technical challenges, there's many ways to solve some problems, but it doesn't matter what language you speak or what culture you come from, science is still science. And I think that's what's kind of fun with like solving this problem, and especially seeing participation from around the world today in solving those problems, because, and I think that's something we can all collaborate on. And now what I'm showing up here is it looks like kind of a spaghetti diagram. There's a lot of lines going different directions, but this is how we defined our technical approaches to solving problems on Mars. And we'll go around the circle here, hitting on these major nodes and different topics for conversation throughout the night. Around from healthcare, life support, space and ground transportation, power generation. We'll cover most of these, if not all of them. And if you have questions on any of them, feel free to ask. So I'm going to transition now and to start asking questions. And let's hear from the panelists, because you didn't come here to hear me talk. You came here to hear the rest of the people talk. So without further ado, let me get into the first question. And if anyone else has questions from the audience, I invite you to open up the question and answer box on Zoom. And there you can type in questions, and I'll see those pop up on my screen And I'll ask them either right as they come up or direct them to one of the panelists as we go throughout the different topics. So please invite you to ask questions there, and I'm more than happy to throw those to the team to answer. So with that, I'm going to stop sharing here so we can see everybody full screen. And when I'm going to ask this first question, and what I'd like is for each of our panelists to give a little brief introduction about what part of the project they worked on in particular. What is their specific background within the technical side right before they answer this question as well. So you can kind of get an introduction to everybody here. So the first question I want to throw out there is, what is the most interesting engineering problem to you, to each of you? And why was that so interesting to solve for Mars? So let's actually start with Dave.
Okay, great. So thanks, Nick, and appreciate everyone attending this evening. I'm CEO of Orbital Transports. We are a Chicago-based space company, and we focus on developing space logistics and orbital infrastructure. Our long-term vision actually is to build the infrastructure that will support the emerging economy of space resources. And so, as you might expect, that is quite in line with this entire project. Today, actually, we are delivering small satellite missions, but we have a path that leads toward that economy of space resources. And consequently, I think for me, the most interesting technical challenge was really understanding the infrastructure that would support a colony of 1 million people on Mars. That's quite a massive undertaking. And just to contemplate the logistics required to support those people, what technologies would be necessary in order to maintain a population that could actually thrive and grow is really an intriguing problem. And that was where a lot of my focus went.
Thanks, Dave. Now let's send it over to Jim Plaxco.
Thank you, Nick. Hi, everyone. I'm Jim Plaxco. In addition to being a digital artist and creative coder, I'm also the Director of Information Systems for the National Space Society, NASA JPL Solar System Ambassador, and a NSS Space Ambassador. For me, the most interesting engineering technical aspects of the project were the interdependencies and the redundancies that have to be built into the system. Because here at home, if our AC fails, our lives are not on the line. But with respect to building and designing a civilization on Mars, failure really is not an option for us.
Yeah, absolutely. You can't just have a leaky roof and be okay on Mars. It doesn't really fly. So let's hear from Konstantinos next. What's your favorite engineering challenge?
Thank you, Nick. I'm a college student right now. I work on a suborbital liquid-fueled rocket that we're developing, which will hopefully be one of the first university-level rockets to get to space. And for the Mars City-State project, I worked on developing a lot of the life support and infrastructure systems along with Dave to support our population. And for me, one of the most interesting aspects of this, I think, was when we thought about how do we make Mars a compelling place to live? Because before, when people moved from place to place on Earth, like for example, from Europe to America, the journey was dangerous, but once they got there, things were pretty safe and stable. But with Mars, not only is the journey very dangerous, but like Jim touched upon, it's dangerous once you get there too. And so we really thought about how do you make a large ecosystem resilient and make it, make it not vulnerable to one thing here breaking or one thing there breaking.
Right. Yeah. And if people know there's security when they get there, they're going to be much more drawn to it, right?
Definitely.
And then Michael, let's hear from you.
Yeah, thanks. So I'm Mike Story. My company is Beckett Solutions. I'm one of the managing partners. We're a technology company with a focus on 3D printing and additive manufacturing. And that really lent well to a lot of what I looked into on the technical challenges is basically what do we need to accomplish in terms of raw materials, or where do we get raw materials? Because it's very expensive to send things to Mars, and there might not be the same materials that are available to us. So how can we get creative in using what's available to us, reusing things that might otherwise be waste? And then I also did a deep dive on the healthcare system, and I found that to be a very interesting challenge. What does healthcare look like in 100 years? Not only 100 years, but what does it look like on another planet? So I'm sure we'll get into that in a little bit, Nick.
Oh, we certainly will. But I think two of you touched on like redundancies and kind of like the challenges with life support. So I'd actually like to have that as our first focus area to talk about. So my question there is, and maybe this is just for kind of bring us all up to the same place, but what are the essential things that you need to live on Mars that maybe you don't consider on Earth? I'm going to send this one over to Konstantinos first.
Yeah, definitely. Thanks, Nick. Well, on Earth, you can go build a house with pretty basic resources almost anywhere you want, barring extremely cold places might not be realistic. But on Mars, if you were to just go build a structure, you would still need a lot more for that structure to really be your home. The air there is not breathable. The air is mostly pretty cold. There's not really a source of running water. So these are all things. This is kind of how we started when we developed the life support system. We said, what are the basics that people are going to need and really reliably, constantly need, and how do we get that started, and then from there build off the rest of the life support system.
So what are like those basic building blocks of life support though, right? Because like on Earth, it's food, water, shelter. Those are really like the givens that you have to like solve for, right? What else do you have on Mars?
Well, on Mars, you need breathable air that has to be produced from somewhere. So we started with ice mining as kind of the very beginning of our overall life support production chain, because with ice, it gives you water and you can also get oxygen from that. And then with food, you obviously need water for your crops. So again, that's where the ice comes into play. So with ice, it really was a good starting point when we thought about the life support system. And from there, we were able to figure out, okay, we have water. What's the next little piece we need to bring this to the next step of life support?
Gotcha. Now, Jim, I want to hear from you too. Which of those, like from life support, whether those things that Konstantinos mentioned or others, like what do you think is like from an engineering standpoint, things that like we really haven't had to solve here on Earth, and what's like uniquely challenging with Mars?
Well, I will point to my parents as an example. Both of my parents grew up on farms. The farms they grew up on, they had no electricity, they had no infrastructure. So they were very much living in a very low tech environment. Mother Nature provided for the bulk of their needs, whether it was air to breathe, water to irrigate the crops, water to drink, water for all the other purposes. Temperature control consisted of, if you got too hot, too bad, and if you got too cold, throw another log on the fire. So all of these things that we don't really think about in day-to-day life, you can still here on Earth lead a very low-tech existence. On Mars, there is no such thing as a low-tech option. And as that technology gets more sophisticated and as we become more dependent upon it, no matter what aspect of a life support system we're talking about, you really do have to stay on top of the design of the system so that they're both durable as well as maintainable, or should I say serviceable. And as you know, as you get more high tech with things, you're kind of at cross purposes here, because high tech is typically not something you think of as being easily serviceable. So there are a lot of push and pull design considerations that will have to be taken into account. And that's obviously a level of detail that I don't believe any team that was involved in the Mars City State Design Competition was able to, get into. So.
It almost makes me think of like, when you buy a new phone or something, you expect it to last you like 2 years now. But 50 years ago when we were going to space for the first time, things were designed to last 50 years, like we're still using some of the same technology that was developed then. And I think like it's definitely putting a different perspective back in mind. And I think that's a very good point that for Mars, we can't really afford to have a disposable culture with anything we design.
Yeah, for two reasons. One reason is obviously you get into the issue of having to manufacture everything from scratch. So things that are very low cost here in terms of material inputs will be very high cost on Mars, which makes it more likely that recycling will be the cheaper option. Whereas here on Earth, with the combination of low cost natural resources and the mass market, which allows you to really build on economies of scale, it kind of helps us to become something of a throwaway culture. So once upon a time, there were actually a VCR repair business was a good way of making money until VCRs became so cheap through mass production that it was cheaper to throw out your old one and buy a new one than it was to pay to have your old one repaired. So the dynamics on Mars are going to be totally different than what we in our daily lives are becoming accustomed to.
If I could, I'd like to follow up on that in a slightly different direction, which is when we talk about what are the things on Mars that we have to think about that we don't think about on Earth. The largest aspect of that, and the one that people really don't think about, is the fact that here we have an entire biosphere that does the recycling for us. It does, it provides air, it provides water, and all of these things just kind of happen without us having to worry about it. Those things don't exist on Mars. And so in order to transplant human civilization there, we need to bring an entire ecology with us. And we need to make sure that that ecology is self-sustaining and that it will continue to operate. Of course, it will probably need help with need the help of humans in order to continue to operate. Unlike on Earth, where it just sort of does its thing by itself, and we happen to be there. Whereas on Mars, we need to intentionally create that biosphere, that ecology. We need to nurture it, and then we can reap the benefits of it. One of the things that is fundamental to an ecology like that, and Jim touched on it, is in fact the recycling of resources. And so that has to be designed into the biosphere that we build on Mars from the beginning. So the concept of throwaway products and throwaway culture and so forth doesn't even make any sense, because you have to think about what are the cycles and what are the loops, where things get recycled, and how and anything that's created and used in that ecology has to go somewhere. And how does it get reused? So all of those things have to be thought about. Whereas here on Earth, we just kind of get that for free.
I'd like to actually follow that thread up with like kind of like a thought experiment just to illustrate to what extent we're talking reuse here. So let's just say like a container, right? I don't know if fast food will be a thing on Mars in 100 years, but let's just presume you have a container that has to get produced. And can we just kind of walk through what are the considerations we have in that supply chain for reuse, and then also like the end life of that? I'm talking like, gaseous byproducts, decomposition, like how do you feed the bugs that are going to do the decomposing? Do you just want to kind of walk through that?
Well, there's two aspects to that. One is, I mean, you're talking about a fast food container, which here on Earth is designed for one use and then it's thrown away. And that use is probably not, for the most part, longer than 10 minutes. That's incredibly wasteful, right? So the first way to approach that is, okay, well, let's not throw away the container. Let's reuse the containers just as containers, right? So maybe instead of having your McPlant burger wrapped in paper, which will get thrown away, maybe it comes in a plastic container, which will get reused. When you're done eating it, you return it to the restaurant, for lack of a better term, and they clean it and they use it for the next guy, right? So that's one level. You alluded to another level, which is sort of the longer cycle of reuse, which is that if we go with, for example, the paper wrapping, that gets thrown into a recycling bin, right? Which then goes into the recycling machinery or process that is part of the overall life support system. So, there has to be a process that breaks it down, separates it into constituent elements, makes those resources available for incorporation into other products or other things. So, you have to look at the reuse and recycling at multiple levels.
Yeah, for sure. Thanks for kind of going down those two different paths on that. And I want to kick the next question over to Mike, because it's kind of on a similar trend. Is like when you talk about breaking something down into its constituent elements for reuse, when you think about like manufacturing methods and like building different products, of course, like 3D printing, like there's some experience on the ISS, like for the space station, for like 3D printing in space. So natural progression that you would do something similar on Mars. First off, I want to ask, like, what are the advantages of 3D printing versus like other manufacturing methods, just to kind of get us all on the same page. But then for 3D printing, like to build plastics, we rely on like, oil, hydrocarbons. Those really may not exist on Mars. So how do we build a supply chain to accommodate that?
A couple of great questions there, Nick. So first of all, for those who aren't familiar, 3D printing is essentially taking a raw substrate and then building up an object layer by layer. NASA has been involved with 3D printing and 3D printing on the International Space Station for a number of years. They sent up several 3D printers. They're experimenting with 3D printing in low and no gravity environments in anticipation of this very idea of habitats on other planetoid bodies and planets. So 3D printing has been around for a long time, 35 plus years. And to answer your question, first about how do we make plastics from hydrocarbons and from oils? Yes, we do. And that's predominantly where most of the plastics that we use in the world come from. But in 3D printing, it's a much more sustainable method of manufacturing as opposed to subtractive manufacturing or producing, say, injection molding, because we're using only the material, only the substrate that we need in order to produce the object, as opposed to subtractive manufacturing, where you start out with a large block of something and mill it down or lay it down or whatever. With 3D printing, we're only using the material that we're going to be used in the finished product. In addition to that, there are all alternative materials that are available to us in additive manufacturing that don't rely on hydrocarbons in order to be produced. So PLA, polylactic acid, is one of the predominant materials used in 3D printing. That's actually made from a byproduct of cornstarch, of corn manufacturing. So it's basically, actually it's funny when you 3D print with it, it kind of smells like maple syrup. It's very sweet. But as long as we're farming in a sustainable method, then we've got a sustainable method of producing finished goods. And then in addition to that, we can take these finished goods once we're done with them and then repurpose them or reclaim them in some method and turn that back into our raw material and then reuse that for 3D printing. So there are various methods that we can use with additive manufacturing that don't have the impact that traditional methods of manufacturing do, and we can reduce our overall material usage. And I forgot what your first question was, Nick.
Well, I think you answered it there. It was about like, what are the advantages of doing 3D printing versus like you said, injection molding or like continuous processing or other manufacturing methods. So I think you nailed that. I'm sold. I think 3D printers seem like the best solution for production there. And we have a question coming in. The question from the audience is, are there any strength concerns with using like plant materials for 3D printing?
You want me to jump in with that, Nick?
Yeah.
So There are and there aren't. With basic materials, sure, there's some strength concerns. You're not necessarily going to get the same strength as you would with a traditionally manufactured part, especially if that part is manufactured out of tool steels or alloys of some kind. But with advantages or with advances in material science that we've seen over the last 5 years, we really have the ability to produce parts that are near to what we can get with traditional manufacturing methods. When we're talking in this case with composite materials, so materials that are a composite of a plastic and some other material, generally a carbon fiber or a glass fiber or a Kevlar fiber, something along those lines that will allow us to recreate, say, 85, 90% of the strength needed with that you would need for producing a part, or excuse me, strength needed in a finished part. So there are strength concerns if you're just talking very basic level materials, but when we start mixing materials and get into more advanced methods of additive manufacturing, a lot of those strength concerns go away. In addition to that, if we can recreate the strength of aluminum at a fraction of the weight, then we've saved quite a bit in terms of cost of manufacturing, material usage, and transportation costs there as well. So those are some of the advantages of using these alternative methods or alternative materials.
Thanks, Mike. I've got a question kind of following that up. I don't know who's best to answer that, but so we've talked about making like things, things that you would support an economy with, but let's talk about habitats. And I see this habitat behind Dave here. Thank you. In terms of like building spaces for people to live, how do we approach that for Mars? Like, what is our proposal 100 years in the future? How are settlers on Mars creating spaces to live in? Who wants to take that one?
I'll field that initially. Our thinking there was that a lot of the habitats would be underground. And it turns out that on Mars, there are lava tubes that just exist naturally. And so there's actually been a significant amount of research done just in terms of what it would take to build habitats in existing tunnels. And it turns out that living underground, while it might sound kind of primitive on Earth, actually works quite well on planets like Mars or even the Moon, because by going underground, you automatically have protection from radiation from the sun and cosmic rays and sources like that. And also it gives you thermal protection so that you're not losing heat off into the atmosphere. So we thought that the initial habitats would start out as underground and might expand as the Marcianes build tunnels, even out of the naturally occurring lava tunnels. There are certainly cases where you would need to build above ground habitats, maybe temporary structures or manufacturing or industrial facilities. Those might be above ground as well. But for the most part, we thought that the habitats would be underground. And I'll tie this actually back to the conversation about 3D printing, because there are some technologies that are being developed even today that use, I'll say concrete. On Mars, what would pass for concrete would be slightly different, but basically 3D printing type or additive manufacturing type technologies for building large scale structures, basically out of concrete like materials. And so a technology similar to that would be used to, for example, line the interior of the tunnels to make an airtight seal so that you could keep air within the structure and so forth. So once you develop those large spaces underground, then you have the problem of building out what would be essentially habitable spaces, living spaces for humans, spaces for manufacturing or industry or just other productive tasks. And then of course, there's also the requirement for what we refer to as green space. And that includes multiple things. Most important is where you're growing food, but also plants generate oxygen. And so that is again, part of the biosphere and the ecosystem. You want to have green spaces because that's generating oxygen. And it also makes the place more appealing and inviting for people to live in.
Nick, can I add on something there to what Dave said? So Dave kind of brought up some of these additive manufacturing technologies for building habitats. There's a number of technologies that are in place today that are being used to build large scale habitats, pop-up habitats that are great for, say, disaster relief, emergency relief, that kind of thing. It's hypothesized, though, that the ability to use some of these materials that Dave had alluded to on Mars when we get there, so using robots, and that would then, say, harvest ice on Mars and combine it with water, fiber, go back to those fibers, aerogels, and then you could lay down that material in layered rings to create these airtight habitats. Also using, say, microwaves to melt and distribute the regolith that's there to form the habitat's protective layers. So there's a number of technologies that are maybe not in development, but are certainly being hypothesized in order to supplement the idea of subterranean Mars habitats.
Thanks for adding that additional detail on that. We've got another question too from the audience, and this one I think, Jim, would be good for you. So you brought up redundancy is one of the more interesting problems to solve, and this question is about with habitats. So if system failure is not an option, what level of redundancy is required?
It's a very good question. It's hard to say without knowing how complex each system is. So as the complexity grows, then the redundancy becomes more of an issue. Very simple systems, though, require minimal redundancy. But with respect to, designing a life support system that will support a large number of people, it's that chain of dependencies wherein you can have, your mean time between failure builds up down that chain. And so with high stakes, there is going to be redundancy, but I don't know how much work has been done along the lines of actually evaluating those systems. Right now, really the only system we've got to use as a benchmark is ISS. That is the one where we're getting our real experience with maintaining a system that has to keep people alive and has been keeping people alive for over 20 years. And then there can be unexpected feedback effects as well that also feed into the whole dependency chain. And I think the shining example of that is the Mars One colony design that was done. That design was reviewed by some folks at MIT that were in the aerospace engineering or the aeronautical engineering department there. And they came to the conclusion that everybody was going to die because they were looking at not just the system, but the sizing of the system and the cycling of the atmosphere between plants, the agriculture, and the people. And they came to the conclusion that the system was out of balance and you'd have a buildup of carbon dioxide, but the Mars colony design had nothing in place to deal with those imbalances. And consequently, it was this team's opinion that the colony would be rather short-lived. So that's not really redundancy, but it is in the sense a backup system that you would have to design to take into account, let's say, unexpected events that may come to pass. So
just to follow on to that, actually, that is a good example of why you need not just redundancies in the system, but different ways of doing the same thing. So we talked about loops and recycling. And one way of dealing with CO2 buildup, obviously, is you have green spaces and plants that convert that into oxygen. But then you might have multiple green spaces that are independent from each other, maybe connected through some tunnels, but they could be separated in case one of them fails. But then you have other backup systems as well. So you have CO2 scrubbers that are designed to remove excess CO2 from the atmosphere. One of the beauties of this sort of recycling system is that excess CO2 actually is not waste. We can use that for production of other useful things. We can turn it into oxygen. We may deal with this a little bit later, but there's a process called the Sabatier process, which converts CO2 and water into methane and oxygen. That, by the way, is rocket fuel. So there's all kinds of uses for these things, and those are all loops in the system that help maintain balance.
And Dave, I'm glad you started bringing up some of those like system flows. I'm going to share my screen again and bring up a diagram that Konstantinos is very familiar with. And I'd like him to just illustrate some of those threads here that I think Jim made the point that, you know, it's not necessarily you're making redundancies in the system, which is a given that you'll need to do, but you're making a system that has a lot of connection points and multiple ways to, you know, create the same necessary ingredients. So I'm showing here the system diagram that our engineering team put together to think about all the interconnected processes here. So zoomed out, you can't see anything because there's so many nodes, everything's connected. But let me zoom in, and Konstantinos, do you want to walk us through some of these exchanges of different elements and processes?
Yeah, for sure. Thanks, Nick. So just to help everybody kind of understand what's going on here, everything that is a rectangular box is some kind of process that we thought of. And everything that is in one of these circular container looking things is a stock of some resource, basically a quantity of some resource. So the whole, and I kind of touched on this before, but the whole life support system really begins with ice mining, which can be seen in the upper left corner. And then that goes into ice processing, you know, filtering it out, making sure the ice is pure. And we get water from that. And that goes through purification. We send it to storage. And from water, we can do a lot. We can get hydrogen, which has a variety of uses. It can be used as rocket propellant, even propellant for ground vehicles. We send some water to the Sabatier process, which Dave just talked about, which gives us methane and oxygen, which are both used as rocket propellant extensively. And the oxygen is obviously needed for breathable air. And in addition, we have the water going into agricultural systems for human consumption, going into bodies of water, which have a variety of uses, which we talked about. And then further down here, we have kind of the entire farming and food production system. So we thought about what are the different categories of food that people are going to need. You know, people aren't going to want to have salad every day for 3 meals. There needs to be some diversity for health and for sanity reasons. And then one of the things we thought would be really difficult to produce ourselves on Mars would be vitamin supplements, because no matter how much we diversify the food chain, inevitably there are going to be some deficiencies that we need to address. And some of those we may be able to somehow source on Mars, and some of them for the time being might still have to be brought from Earth.
Yeah, thanks for walking through that. Yeah, all these systems too, you can see, if I just point out some blue lines as well, this is where, wait, is that, never mind, I'm going to take that back. I misread that part, but yeah, there's so many interconnected systems here when you look at, you know, in life support, water reclamation, manufacturing, and power generation, everything's connected. The waste from one system may be an input to another. Right. And having this like really connected system is so valuable, because on Earth, right, we use like rivers as heat sinks. We don't really think about what to do with excess heat. Heat is a problem, but in fact on Mars, heat's actually something you need, because it's what the average temperature is a cool, like, what, I think on a really hot day it gets up to freezing, like 30 degrees Fahrenheit, something like that.
Well, if you're on the equator and it's summertime, your feet will be very comfortable, like maybe 60 degrees, but your head, you better be wearing something really warm, because your head will be freezing. The temperature drops off quite rapidly as you begin to inch away from the surface.
And that's because,
Thin atmosphere.
mhm. So inside your habitats, you'll be better off. Just once you step outside, right, into those uncontrolled environments. And you know, we've been talking a lot about living on Mars, but I want to talk a bit about, oh, actually, before we deviate from that topic, I see there's a couple questions that came up around the topic of like feeding a population and what we just talked about. So let's ask those real quick. So how much infrastructure is needed to grow food for 1 million people? Like what kind of magnitude and scale are we talking about here?
A lot. Well, first off, in terms of, it depends on how many calories per day you want to have available for your population. And from there, you then have to make sure that you have an adequate air supply with the proper mix. You need a water supply, you need a nutrient supply, and you need grow lights, which means you're going to need a lot of energy. Here on Earth, agriculture today is a very energy intensive industry. On Mars, it will be much more so because nothing will be free. Everything will be manufactured, from the water that's used for irrigation to the light that's used for photosynthesis.
Another question about growing is, will you have typical growing seasons on Mars? Or is there a way to just optimize production to be continuous, right? Since you don't actually have seasons in like the sense that we have here.
Yeah, production would be pretty much continuous. As Jim just mentioned, the lighting required to grow food and really all of the plant species in general will have to be artificial light, simply because there isn't enough sunlight, and also a large majority of the habitats would be underground anyway. There are some designs for capturing and concentrating solar energy, but really in order to grow food, we'll need artificial light, which requires, of course, power to support that. And what that means is that you don't have to worry about seasons per se. So we can basically do agriculture year round and stagger crops and so forth as necessary.
And you know what that means? You're going to need a lot of light bulbs.
Absolutely. I actually just heard a fun fact. Plants are actually very inefficient at harvesting sunlight. So it'd actually be more efficient on Mars, because it's further away from the sun, to have a solar panel collecting solar light and then turning that into electricity and powering a light bulb, like an LED light, to then give light to the plant for photosynthesis. That's actually more efficient than the plant absorbing the sunlight directly. So it kind of like removes any necessary sunlight input for plant production. You can grow whenever you want. Actually, it's better that way. So I want to, there's a couple more questions here that I think we'll cover in one of the next topics here. But I want to step away from the surface of Mars for a moment and talk about the above Mars, right? So if we're going to go to Mars, presumably we're going to have to go through space to get there. And what does the space economy and technology look like to sustain life on Mars?
So we made certain assumptions about that. And one of those assumptions is that in order to colonize Mars, we have to have a spacefaring civilization, which means that anybody coming to Mars is going to be coming from space. And that has some interesting implications. First of all, any sort of space infrastructure, I won't say we get it for free, but it kind of comes with the program. And that space infrastructure includes things like using Phobos, one of the moons of Mars, as a space station. And so we determined that that would be a useful location actually to build a waypoint for fuel depots to refuel spacecraft that are departing Mars or going to other destinations. And it also serves as a useful base for actually constructing spacecraft in orbit. And given the 100-year time frame, we decided that At the time that we're talking about, Mars would just be starting its spacecraft production capability, and that there would be a space yard actually in space, not necessarily on Phobos, but associated with Phobos. The space-based infrastructure also has other implications. One of the first things that would most likely be deployed around the planet would be a satellite constellation for communication. And so there would be communication basically available anywhere on Mars. Similarly, there would be, I hesitate to use the term Earth observation satellites, they'd be Mars observation satellites, but basically remote sensing satellites to collect data about what's going on on Mars. And so all of that data and communication capability would be available almost, I won't say immediately, but it would be part and parcel of the Marcian civilization. One of the other implications of a spacefaring society is that Mars is not the only place where there are humans off Earth. We assumed that there would be a lunar colony. Most likely it would be older than Mars. And whether there would be more people on Luna than on Mars is unclear, but there certainly would be a lunar civilization. Similarly, there would be asteroid mining activities happening, certainly on near-Earth asteroids, and with the Martian civilization be postulated that near-Mars asteroids would also be targets for resource extraction. It also means that Mars becomes essentially a jumping off point for explorations deeper into the solar system. So there could be initial asteroid mining of main belt asteroids happening, and potentially other deep space exploration happening as well. I'm sure there's more, but that's a good start anyway, to think about the space-based infrastructure that would be there. Konstantinos or Jim, do you have other thoughts?
Well, one thing, if I could jump in here, Dave, you mentioned space-based infrastructure and some of the manufacturing and using near Mars asteroids. One of the things I think we haven't included in the diagram that we showed before, actually, the system diagram, was space-based solar power. And we thought about, actually, in a good amount of detail, how to use asteroids to produce these satellites. Because one of the things Dave mentioned was that it's a lot easier to have stuff in space that's made in space instead of making it on a planet and then bringing it up into space. And with space-based solar power, it's an additional method of power generation, which then adds redundancy to the surface settlement on Mars.
And actually, just to follow on your comment about space-based manufacturing, certainly the asteroid-based resources would be good sources for that type of manufacturing as well.
Definitely.
Now I want to bring it back down to Earth and talk about
or Mars.
Oh my gosh, back down to Mars, and talk about the human element and some of the challenges specifically related to humans, not necessarily keeping people alive, but like what makes us more than animals. And I think there's a question from the audience that I think kind of gets at one of those sort of challenges. And the question is, how much agency do you imagine citizens will have in terms of balancing their individual freedom versus the need for certain professions, right? We've identified a lot of like essential businesses. So to what extent will people on Mars be able to choose their life?
I'm just wondering if that question maybe can be deferred to the next webinar, because that will be addressing a lot of those questions very, very directly.
I will copy that as well for that group too. It's a different context, kind of different thought process as well, but I really like that question, right? Because it gets it a little bit more of, you know, we're not just animals that we're trying to keep fed and warm enough to survive, but people need to go there for a reason. Yeah, I guess I don't have an answer to that either, but if I can use that question to pivot into healthcare, I think that's important to address here while we're on the subject of people. So Mike, I want you to kind of give us a rundown of what healthcare on Mars looks like, because you know, like Konstantinos said about getting different reagents. Like it's tough to get vitamins, but that's not, that's only just a piece of like health. Tell us more about like healthcare and what you're imagining for like the future on Mars with that.
Yes, healthcare is an interesting challenge when it comes to hesitate to use the term, but a disconnected society from a larger overall group. There's a lot of factors that go into determining what are the needs of the individuals, what are the needs of the health of society at large. And so a lot of the thought process behind developing a healthcare system for Mars is more of a health maintenance system that it's going to help us provide for the overall health and well-being of the society and the Martian citizens. In that there's a focus on public health and overall healthy lifestyle. Preventative medicine is going to be paramount. Physical activity promotion, lifestyle education, home health, nutritional education and support, mental health promotion. All these are factors that are critical in maintaining a healthy society. Things that are going to be the focus of the healthcare system. From there, now we're looking at a more technologically advanced healthcare system. We're going to be using a lot of machine learning in order to diagnose issues before they become problems, both on the individual level and on the societal level and the environmental level, right? There's going to be a need for environmental health maintenance, for countermeasure systems to provide for the need to avert any disasters that come into play. The need for AI and robotics as part of the healthcare system. So we figure that a lot of healthcare will be performed in home. In fact, that'll be the preferred method. Auto docs, perhaps you've heard the term, the ability for a robot to perform minor procedures and surgeries in home. We fully expect that will be developed by the time that we reach Mars. Advanced medical care, both in home and in central locations. And then you mentioned, Nick, the supplies side of things. So the ability to produce pharmaceuticals, the ability to produce vitamins and other medicines, medical supplies, PPE, disposables, surgical supplies, home healthcare supplies. A lot of that ties back into our recycling and reusing of components. A lot of that will be will repurpose raw materials or will repurpose other goods from other technological processes. We'll look at doing, instead of having a generic multivitamin that would be applicable to 90% of the population, we'll look at producing drugs on demand based on someone's own body chemistry and individual health makeup. So the need for those systems are all paramount as we look to individualize healthcare while at the same time maintaining an overall healthy Martian society. So I know that's a lot to throw out, but that's kind of a 30,000 foot view of healthcare on the Mars society.
Thanks for that. We actually got quite a few questions that came through while you were talking there. So I'm going to throw a couple back to you or the team as well. So first question is about exercise. So, and actually there's another one about like gravity, and gravity being like a third of what is on Earth. Isn't exercise even more important? And how do you actually convince people to do that when it's hard enough to get people to do that here on Earth?
Yeah, I'll jump in there. It's certainly a challenge. I think we've all probably lacked or probably lagged in our exercise, especially during, this is kind of a little taste, right? We're all living in a lockdown society and might not have access to the resources, the societal, the community resources of gyms and health groups and so on and so forth. So education is going to be a premier focus, paramount importance in order to make sure that society is fully healthy at the optimal level. Now, you can't force somebody to exercise, but we expect that people that are going to be traveling to Mars to live in this society have an innate understanding of what it takes to live in space, and that it's going to be, these people are going to be healthier, more healthy in general. Just an assumption, but it's one that we figure that we could make. What was the other question there, Nick?
I think you answered that one. The next question, though, is about just healthcare in general. And I think we covered this in our last session, the economic panel. But the question here is, how would healthcare in general just work? Not necessarily like what sort of things that people engage with healthcare on, but like, is it funded by individuals, corporations? Is it a public good? And like, would it be more expensive? Does anyone want to take this one specifically? Jim, you were actually on that panel last time. Can I field the question to you?
Sure. And I'm going to totally go politician here and answer another question that's also in the chat, but I think it kind of ties in with this question. And it was the question about, is there going to be sufficient capacity for ice mining to support the population? So that becomes a question of how are we allocating our resources on Mars? And it brings to mind a very good story that about 70 years ago, 60 years ago, the US Army built a city underneath the Greenland ice sheet. And they used a portable nuclear reactor on site to provide power. So these guys are surrounded by ice. What was the most severely rationed item, consumable item? It turned out that it was water, because they did not have enough resources to meet all of the base's needs and simultaneously supply everyone with as much water as they would have liked to have consumed. So it is going to, I think, be the same thing on Mars. We live in a universe of scarcity. And I think that the degree of scarcity is going to be more pronounced on Mars, given that everything will have to be manufactured. So
just to be clear about that, there certainly is enough water on Mars. The question is not whether or not the resources it's there. It's an issue of extracting them and distributing them.
Right, the energy resources that are available. So someone's going to be sitting down and they will have to decide how to allocate resources, whether it's to offer high enough salaries to induce people to take those jobs that are critical, but that maybe no one wants to do, or to work in the medical profession. And so I am much more, I'm not sure what word I should use. I don't want to paint an overly rosy picture that we're going to be creating a utopia on Mars where everybody has everything that they need. It's not true here. It will be less true on Mars, is my perception, unless our technology makes substantial advances. Because if we think about how people lived 200 or 300 years ago and look at how we live today, technology has made that possible. So we're looking 100 years into a future, and it's hard to say, you know, where technology will take us. So a rather long and oblique answer to the question.
But quite practical too, right? Yeah. And Konstantinos, you wanted to follow that up?
Yeah, I wanted to add in, so Jim talked about the ice mining and how there is enough water on Mars to support the type of life we're discussing here. But one thing we did consider when planning this was that a lot of the water that's harvested will be turned into rocket propellant. And once that's burned by a rocket, it never comes back. It gets discarded into the atmosphere basically as a different gas. So it is important for the civilization on Mars to really recycle as much water as they can and keep it in a closed loop, just because otherwise it might be too difficult over time to still harvest enough for rocket propellant and for life support. So to make it easier for the amount of water being extracted, it's really important to keep water for life support in a closed loop, because all the water being used for rocket propellant is discarded.
Great point. And looking at the clock here, I think we've got time for one more question. And this one, oh, just thought another one sneak in here on the topic of ice. How long do we think the ice on Mars will last for 1 million people? That question, my understanding of it is it like how long would it last in a closed loop? or how long would it that exist in the
As I said before, there is certainly enough water on Mars. Yeah, there will be losses, but you can sustain a fairly large population just on the water that's being recycled. So yeah, we'll need to continue mining ice to replace the water that's being lost and to account for growth. But then because the overall stock of water is being recycled through the biosphere, supporting a population of 1 million people or more potentially is quite feasible for a long period of time. And long period, I mean hundreds of years, potentially even longer than that.
Yeah, over the decades, we've had something of a pendulum with respect to Mars. Our perception of Mars went from it being a very water-rich planet to
with canals,
a desert world, back to okay, they've got water. And curiously, during that Mars is a desert planet, how will we survive there without water? There were actually proposals by people that we should just take the hydrocarbon-rich asteroids and set them on a collision course with Mars. So rather dramatic solution to the problem, but it has been proposed.
I would use water-rich comets instead of asteroids, but the same concept.
Yeah. All right, so last question I want to throw out there is actually kind of bringing it back to Earth for real this time. So we're talking about like technology that we're hypothesizing may exist in 100 years or already exists today, and we're just taking it kind of the next step. Why do we care? Like, why do we care about solving engineering challenges for living on Mars and building a society in the future on Mars? And I'd like to hear from each of you on that. So Jim, you open your mouth first, go ahead.
Because every engineering challenge we overcome becomes another resource that we have available to ourselves for what may happen to us in the future. Now, when we sent probes to Venus and we began to study the upper atmosphere of Venus, particularly there was an interest in the chlorine chemistry. Nobody could have foreseen at that time that the attempts that were made to understand the chlorine of chemistry would lead to the discovery that the chlorofluorocarbons that we were using for our air conditioning units were destroying our Earth's level of ozone, which protects us from solar UV radiation. That was an entirely unforeseen benefit that no one would have predicted. So new environments give us new engineering challenges. We come up with new solutions, and they become new solutions in our arsenal of solutions to whatever future problems may rear their heads.
And just to elaborate on that point slightly, the technologies that will be necessary to build self-supporting, self-sustaining, recycling ecosystems on Mars will be a significant technology for life here on Earth. And we're desperately in need of those kinds of technologies, but there's not a huge incentive to develop them because, well, we have this biosphere that kind of supports us. On Mars, that biosphere doesn't exist. We have to build it. And so we'll learn a lot about what it takes to actually have a self-sustaining, self-supporting biosphere. And that will certainly be something that can be returned back to Earth. And so those sorts of biological or biotechnic or ecotechnic technologies are potentially a huge export from Mars. But as to the larger question of why Mars at all, for myself, I consider it a biological imperative that life from Earth will expand and settle the entire solar system, Mars being one of the places in the solar system. So it's a reasonable target for early settlement just because it's somewhat Earth-like. There may be other places that might be better, but it's reasonably accessible. So that's, for me, it's out there and we're going to go. So let's plan on how we're going to do it.
And just to quickly follow up on a point that Dave made, We have Biosphere 2 here on Earth. In one sense, it was regarded as a failure because they did not succeed at what they had attempted to do. But on the other hand, you can regard it as a huge success because it generated a couple hundred scientific papers on new insights about what not to do. So we learned from that failure.
Yeah, Biosphere
Absolutely.
Biosphere 2 was not treated well in the press because they expected that the claims that 8 people would live in a completely enclosed ecology for 2 years didn't happen. So it must have been a failure. But my God, they learned so much about building sustainable ecosystems. And as you say, there's so much knowledge that came out of that.
Konstantinos or Mike, would you like to add anything to that kind of point about why we care about Mars and solving the engineering problems there?
Yeah, sure. So Dave kind of touched on what I wanted to say when he mentioned that it's our biological imperative to expand human presence in life as a whole throughout the solar system. But additionally to that, and this kind of gets thrown around a lot and then made fun of by society, but it is necessary as a backup to Earth. And a lot of people will say, well, maybe, but right now there's nothing that is making our existence on Earth about to go extinct. You know, it's not like there's some asteroid about to hit us in a couple of years, as far as we know. However, our estimate when we did this project was that it would take close to 100 years at least to truly become self-sustaining on Mars. So if we wait until there is a real need to create a backup hard drive for humanity, it is too late by then. It needs to be done and ready to go before something like that is on the horizon.
And I'll just paraphrase John F. Kennedy in his speech when he said, "We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard, because it's a goal that will serve us and organize and measure the best of our energies and skills. And because that challenge, that this is one challenge that we're unwilling to postpone." Don't quote me on that. Anyway, to that end, we choose to take on these challenges not because they are easy, but because they challenge us and they push us as human beings, and they bring out the best in us. So for us, the designing and solving the engineering challenges of going to another planet and living on another planet is something that will help evolve us as a society and as individuals, and should help propel our culture into the next century. So I'm excited about the opportunity that we have for space travel in the next 100 years.
Mike, you got me pumped up. I was just thinking here, looking at my screen, I see five of us who are part of writing this paper, and I have a team of 17. But in this one, very narrow focus of solving the problem of the future, there were actually 175 teams from around the world who submitted papers for this competition. So there's a lot of people all around the planet on Earth thinking how important it is to solve these problems, and I know we will. And it's very exciting to work towards that future and to really make that happen. And with that, I'm looking time check, and I think that's all we've got for technical challenges and discussion here tonight. And I thank so much for our 4 panelists here for giving us their thoughts and research and expertise on the topic of solving these engineering challenges on Mars. And I'm going to bring back up the presentation here to talk about our next presentation. And let me show my screen here. So the next presentation we have, it's called 1 Million Marciane, Societal Challenges. And this is where we'll get into the kind of solving some of the human problems. What does a culture look like on Mars, especially when you've got people coming from very diverse backgrounds on Earth? What are the political systems? Kind of what is the aesthetic of living on Mars from like an art perspective, and also like how is that reflected in the activities that people do? So I think that'll be a very fun topic as well, and completely different than like the technical side. And that's on December 8th, and you can find that on Eventbrite, or follow NewSpace Chicago and get on their distribution list, and you'll get any updates about future webinars. And then also coming down the pipeline in January, the final date TBD still, but that's the state of the space industrial base, and Dave Hurst will be leading that conversation. And finally, like I said at the beginning, NewSpace Chicago is it's a 501c3 organization. So we are very excited to accept any donations that you may want to give to the organization. They're tax deductible and they help support entrepreneurialism in the space industry in Chicago and the Midwest. And there's many different ways to become a sponsor. You can just donate. You can go to the website, newspacechicago.com/donate. You can become a different, like an event sponsor for the price of $250 an event. It can be included in marketing. You see here the different benefits you get from being an event sponsor, or to be a premier sponsor and sponsor on more events throughout the year and really partner with the organization to help promote space science, technology, and entrepreneurship in our area. And with that, I just want to thank you all for coming here. Thank you so much for joining me and our panelists and all the attendees here to talk about space and really just to become excited about what the future can hold and the future that we can create. With that, I'll see you all in a few weeks.
Good night, everyone.